Now, one very important effect that is the result of the fact that molecules have three-dimensional shape rather than a simple two-dimensional configuration as we use for Lewis structures is that molecules themselves can have polarity and dipoles just like bonds can. So let's look through that quickly. Because each individual bond has a dipole moment, each molecule will have a net dipole moment, where the net dipole moment is simply the sum of the individual bond dipoles. So what does this look like exactly? Let's take water as an example. So in water, the individual OH bond dipoles point towards oxygen as the more electronegative atom. And so we can see them drawn here. The net dipole moment, however, is the sum of those two. And if you're familiar with vectors, dipoles sum in the same way. If you're not, just follow me and we'll sort of explain how you add these together. But the net dipole moment is simply the addition of the two individual bond dipoles. So in this case, I have one pointing from one way, one pointing from another. They have a vertical component and a horizontal component. Their horizontal components cancel each other out because they're pointing in opposite directions, but the vertical components are both pointing in the same direction. So the net dipole is simply pointing straight up the molecule. What that results in then, if we draw this in more of a map shape, is that one whole side of the molecule will have a partial negative charge, and one whole side of the molecule will have a partial positive charge. Just like in bond dipoles, one side of the bond has a negative, one side of the bond has a partial positive charge. The net dipole means that molecules can have the same thing, where one side of the molecule has more of a net charge, a net negative charge, and the other side has a partial positive charge to it. Let's show this in a couple other examples and extend our terminology a little bit. So a molecule that has a net dipole resulting from polar bonds is known as a polar molecule. Now note that it has to have polar bonds. All molecules, unless they are symmetrical, which we'll get to in a moment, have a net dipole moment greater than 0, but not all of those will be polar molecules, only those that have a net dipole moment resulting from polar bonds. So let's do maybe another example here with CO2. In CO2, oxygen is the more electronegative atom, so both carbon-oxygen bond dipoles are pointing towards oxygen. But the molecular shape, as we would know from going through the VSEPR model, is a linear shape. And so those two dipoles are pointing exactly opposite each other with exactly the same magnitude. And as a result, what we have then is an overall dipole moment of 0. This molecule has a net dipole moment of 0. Essentially, there's no partial positive and partial negative ends of the molecule. And we can still look at its this map here is simply showing the electron density. And we can see that the two ends both have maybe more of a negative density to them because of the individual bond dipoles, but there's no single end of both ends of the molecule have the same charge. There's no net directionality to the charge in the molecule. What results from this then is that CO2 is a non-polar molecule. So we can have polar or non-polar molecules, just like we had polar or non-polar bonds. So let's go through a few examples of this. So if we look at BF3, for example, in this case, we have polar bonds. Well, fluorine is significantly more electronegative than boron. The electronegativity difference is 1.5, so that would be a polar bond. But they are all pointing in opposite directions. There is symmetry, and if you added up the vectors of all of the bond dipoles, they will all cancel out and give you an overall dipole moment of 0, and thus the molecule is non-polar. HCl, on the other hand, Well, it turns out that this molecule only has one bond, and so the bond dipole is also the net dipole for the molecule. So this is a polar molecule because the electronegativity difference between hydrogen and chlorine is great enough to make it a polar bond. Something like chloroform here, CH3Cl, in this case, there are some bond dipoles that are not drawn between carbon and hydrogen, where carbon is actually more electronegative. So all of the bond dipoles from each of these are pointing towards the carbon. But the electronegativity difference between carbon and hydrogen is less than 0.5. So this is those are all non-polar bonds. And so although they do contribute to the overall net dipole moment, it's really the chlorine-carbon bond, which is exactly at 0.5. We would consider this to be just above the threshold to be polar, or right at that region. But the fact that we have a bond that we would consider in this case to be polar, and if we do the net dipole moment, what we'll see is all of the carbon hydrogens are all pointing inwards. Their horizontal component will cancel, but they're all pointing inwards and upwards. So there's a vertical component to it, which then also matches the vertical component of the carbon-chlorine bond dipole. And we do end up with a polar molecule for this. Now, it may not be a very strongly polar molecule because we have 3 non-polar bonds and then 1 bond that we only barely consider to be polar at 0.5 difference between the electronegativities. NH3 is another example here. All of the nitrogen-hydrogen bonds, those all are pointing towards nitrogen for the bond dipole, and they're all polar bonds. And so since they're all pointing inwards, the horizontal components cancel, but they're all pointing inwards and slightly upwards. So our net dipole moment for this actually is pointing straight up, just like it was in the CH3Cl. And this is a polar molecule. Lastly, carbon tetrachloride, that molecule that we visited at the very beginning of this chapter, we have 4 polar bonds, but they're exactly symmetrical. They're all pointing out towards the chlorines, but it's all pointing in different directions symmetrically throughout the molecule. And if we added up all of the vectors of their bond dipoles, they would cancel out to 0. And we have no net directionality to the charge in the molecule. And although every single individual bond may be polar, the molecule itself is non-polar. So let's go through a few examples. Really, the summary before we get there is just that asymmetrical molecular geometry means that I will have a net dipole moment and that it'll be a polar molecule, providing that I have polar bonds, at least one polar bond. If I have a completely symmetrical molecular geometry, then by default, whether I have polar or non-polar bonds, I will have no net dipole moment and it will be a non-polar molecule. So predict whether each of the following molecules is polar or non-polar, and if it's polar, we need to draw the net dipole moment for each molecule. So here we really need to draw the structures, but we need to draw them with their molecular geometry taken into account. If I draw this first example here of CH2Cl2, I could draw it if I was simply drawing the Lewis structure. I would draw it something like this and say, well, it looks like all of the bond dipoles are going to cancel each other because there's going to be 2 carbon-chlorine bond dipoles that are pointing towards chlorine, but those are exactly opposite. And there's 2 hydrogen-carbon dipoles that are pointing towards carbon. Those are exactly opposite. No net dipole. This is a non-polar molecule. But that neglects the fact that the 2 chlorines are not directly opposite each other. The geometry is not linear there. We need to draw this in its actual geometry, which for 4 electron domains, all of them being bonding, the molecular shape is a tetrahedral geometry. So what this looks more like is chlorine. And then in the same plane, we can have chlorine. And then hydrogen can be coming out of the plane towards us. And the other hydrogen going back out of the plane away from us. The bond angles between all of the different atoms and bonds is 109.5. Or roughly thereabouts. So in this case, if I draw it more in this way, I can see Perhaps it will help to switch colors. But I can see that the bond dipoles, the individual bond dipoles, are pointing towards the chlorines as the more electronegative atom, but those clearly don't cancel each other out. And the two hydrogens are pointing in towards carbon, and these clearly don't cancel each other out. Now the two carbon-chlorine bonds are polar, and so they have a greater influence on the net charge. But essentially, if I were to take these two, and if anytime that I have two bond dipoles, the net dipole is going to lie in between the two. So I can draw the net dipole moment for this as simply being drawn in this direction, where this side of the molecule up here is going to be the partial negative, and this side on this side will be, this side on the left will be the partial positive for the molecule. Let's take a look at SO3. So if I remember SO3, I can draw that, and I'll just draw one of the resonance structures. It has multiple. And I will draw it in its trigonal planar geometry. So this has 3 electron domains around the central sulfur. It's 120 degrees between all atoms, and it's symmetrical the whole way around. So the dipole moments for the individual bonds point towards the oxygens. But remember that I've got 3 different resonance structures. So the bottom oxygen could be the one that's double bonded, or the right oxygen could be the one that's double bonded. And so the magnitude of those individual bond dipoles is identical. It's symmetrical the whole way around. So we would say that this is a non-polar molecule with no net dipole, or net dipole of 0, non-polar. Up above CH2Cl2, we would have said was a polar molecule. Finally, I get to SF4, and to save us a little bit of time, I'll draw that out. I think we dealt with that previously. So fluorine, 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 and then a lone pair. Dipole moments are pointing towards the fluorine as the more electronegative atom, sulfur being the most electronegative. So these two in the vertical plane are going to cancel each other out entirely. However, these two in the horizontal plane will not cancel each other out. They have horizontal components. One's pointing one way, one's pointing the other. The net dipole is going to be in between, and so my net dipole for this molecule is going to be pointed in that direction. And this is how we do net dipoles for molecules more than just bonds, where we can actually sum up the dipoles of the individual bonds to form a net dipole and determine whether a molecule is polar or non-polar. In this case, SF4 is a polar molecule. It has net dipoles resulting from polar bonds.